Okay, so hi everyone. So welcome back to this new video in this sliding window series. So today in this video we are going to solve this problem from CSES problem set that comes under the sliding window section and goes by the name sliding window minimum. So let us start with this problem without wasting any time. So the problem reads like this, that you are given an array of n integers and your task is to calculate the minimum of each window of k elements from left to right. So in this problem the input data is large and it is created using a generator. So in the input the first line contains two integers n and k, that is the number of elements and the size of the window, and the next line contains four integers x, a, b, c, that is the input generator parameters. So here it is written that the first element of the array will be equal to this x and the remaining elements will be generated using this function here. And then finally in the output you have to print the XOR of all the window minimums. So this is the constraint here in which the value of k and n can go up till 1e7, the value of x, a, b can go up till 1e9, and the value of c can go up till 1e9. So the constraints are pretty high here, and this is the example given for which the expected output is this and the explanation for it. So this is the question. I hope you got this. So the question is asking us a simple thing, that for a given array, for every window of size k you have to compute its minimum and take XOR with each other, and whatever the XOR result will be there at the end after taking the XOR of all the minimum of each window, you have to print that result, that is an integer. So this is the problem here. So let us move forward and see what logic we will apply, right? So let's move forward now. So consider this example that I have considered. So suppose after using the generator function, this is the array generated here, right? So I have considered this example by myself. This is not given in the problem statement, so that you can understand better, right? So in this example that I have considered here, the value of n is 8 and the value of k is 4. That is a total of 8 array elements are present actually, right? But since I want to deal it with one based indexing, so here I have added a dummy value of 0 at the 0th index, and also the window size is 4. That is, we have to compute the minimum for each window of size 4 like this, right? So here I have marked each window with different colors, and on top of that I have written the expected output, that is the minimum of each window. So for the first window the minimum is 1, for the second window the minimum is 1, and so on till the last window. So our task is to take the XOR of all these window minimums with each other and finally print the output. So if you take the XOR here for each of these minimums, then this one will cancel with this one, this 2 will cancel with this 2, and finally this one will remain only, right? So the answer should be 1 for this example. So we will see at the end that if we are able to get our answer or result as 1 or not, right? And also the total number of windows that should be present here should be equal to n minus k plus 1, that is 8 minus 4 plus 1, that is 4 plus 1, that is 5. So 5 should be the total number of windows. And here also if you see, then here I have drawn a total of 5 windows. So the first window is this, having a size of 4, then the next window is this, right? Then this is a third window, this is a fourth window, and finally this is our fifth window. So total of 5 windows are present, which can be derived using this formula of n minus k plus 1. So this is our given nums array here, and now we want to solve this problem for this example. So now let's move forward and see what we will do. So if you see, then what we want, so since we want the minimum value, so we will use such a data structure here in which the minimum element of the current window will always be present at its front, right? And in order to do this, DQ can help us very easily, because we know that DQ supports 4 types of operations, that is pop front, pop back, push front, push back. So suppose this is our DQ data structure, and this is the front of it and this is the back of it. So if someone wants to pop out any element, that is to remove an element from the DQ or retrieve an element from DQ, then it is possible from this side as well as this side. Similarly, if someone wants to add an element to this DQ, then he or she can add it from this side as well as from this side, that is push front and push back. So all of these 4 operations are possible in this DQ, and we will use this DQ only in order to store our minimum element at the front side every time, so that whenever we want the minimum element of the current window, we will always go to the front and take out the minimum element. And in order to do this, we will use some logic, and you will definitely understand how this logic will be successful here. So let us move forward now and see how can we use this deque in order to store the minimum element at its front always, right? So let's move forward and see how this will help. So since ultimately I have to return an integer which will include the XOR of all the window minimums. So here I have declared this variable here, that is result initially having a value of 0. And before moving forward, you must be knowing two properties at least, that is the XOR of any element with 0 is equal to that element only, and also the XOR of any element with itself is equal to 0. So once you know these two properties, let us move forward now. And now we will handle our very first window for the first time, that is we will handle the first window separately, right? So this is our first window. So let us now start and try to see how we will use this deque in order to solve it for the first window first. So as you know that in order to solve the problem for the first window, we always start from the first index and go till the kth index. And since in our case the value of k is 4, so we will go from the first index to the fourth index, right? So now suppose we have started our iteration here, and now we are standing on the first index here, which is having a value of 5. So now what we will do is, since initially our deque will be empty completely because we are just starting our operation, so initially our deque will be empty, so there is no element to compare this 5 with, right? So it means that this 5 can be the minimum element of the current window, but we don't know as of now. So what we will do is we will simply push this 5 into the deque. So here I have pushed this 5 into the deque, right? So I have done a pushback here so that this 5 has entered this deque. So once this 5 has been entered, now we will move forward with the next index. So we will increase the size of this window, and now we will be standing on this second index, which is having a value of 1. Now pay attention what will happen. So now we know that we are standing on the second index, which is having a value of 1 and is a part of the current window, right? But this 5 was also a part of the current window, which is being stored at its back right now, right? So since this 1 is also a part of the current window and this 5 is also a part of the current window which is stored here, so we will see that this 1 is definitely less than this 5, which means that it is possible that this 1 can be the minimum element of the window that we are doing this operation for, but this 5 can never be the minimum of this current window anymore, right? Because in the every window, including this current window, as long as this 5 will be present, this 1 will also be present, and as long as both will be present together, 1 will always be less than 5, and hence the minimum of any window, this 5 can never be, but this 1 can be, right? So since this 5 can never be the minimum of any window now, because this 1 has come now, so it means that there is no purpose of storing this 5 in the deque anymore. So we will just do a pop back here in order to remove this 5, right? So once this 5 is removed, we know that 1 can be the minimum element of the current window, so we will push a 1 here, that is a pushback 1. So in this way 5 has gone from the deque and 1 has came, right? So this is the status of my deque after operating on the second index. And now we will increase the size of the window and we will reach the third element. So now we are standing on the third index, which is having a value of 2, right? So we will see and compare this 2 with this 1. So since this 2 is greater than 1, so it means that this 2 as well as this 1 are both part of the current window, right? This 2 and 1 are both of the part of the current window that we are trying to do the operation for, that is from 1 to k. So both are the part of the current window, and this 1 is less than this 2. So it means that for this current window, this 2 can never be the minimum, right? Because this 1 is less than 2. So for this window, this 1 might be the minimum, but this 2 cannot be the minimum, right? But there is a possibility that when this 1 will leave this window or will be excluded, this 2 can be the minimum of the next windows, right? So that's why we will simply insert this 2, that is a pushback, so that both 1 and 2 stays in the deque. So why I have done this? Because now we definitely know that this 2 cannot be the minimum of the current window because 1 is present here and 1 is less than 2. But it may be possible that in future this 2 becomes the minimum of the remaining window. So that's why we have just inserted it in the right position, right? So this is the status after processing the third element, and now the window size will finally become equal to k, that is we will be standing on the fourth index having a value of 4. So now again we know that this 4 is a part of current window in which both 2 and 1 are already present. So now in the current window 1 is present, 2 is present, and now 4 is also present. And since this 4 is definitely greater than this 2, right? Or this 2 is definitely less than this 4. So we know that this 4 can never be the minimum of this current window. But it may be possible that in the future when this will be our window, then 4 might be the minimum element. We don't know. So that's why what we will do is, to consider this case, we will simply store this 4 into our DQ. That is, we will do a pushback of 4. So that when earlier 1 and 2 was present, now 4 will also be present. So this will be the status of our DQ after processing the first window. So I hope you got what I just did. So what I did was very simple. So initially our window was this, and the first element we encountered was 5. So there was nothing to compare 5 with. So we just did a pushback of this 5 and stored 5. But when this 1 came, so we know that both 1 and 5 are now a part of the current window, and 1 is definitely greater than 5, smaller than 5. So 1 can be the minimum element of the current window, but this 5 cannot. So we just erased this 5. And after erasing this 5, we just push back this 1, right? And when we moved forward and this 2 came, then we knew that this 2 is still greater than 1. That is, it cannot be the minimum of the current window, but it can be the minimum of the next window. So we just stored it for future purpose, and same thing we did for this 4 as well. So after doing all these 4 operations, this was the status of my DQ, in which these 3 elements were present, and this was removed because we were very sure that this 5 can never be the minimum of the current window or remaining window. So we just erased that initially only. So since this is the status of my DQ, and you can see that all the elements here are filled in sorted order in this direction, and we have done it purposely so that the minimum element will always be present at the very front, right? So finally only those elements will be present in the DQ in which 1 is the minimum of the current window, which will be present at the front, and the remaining elements, which is 2 and 4 here, can be the minimum element of the remaining windows or the next windows, right? So this 1 is the minimum element of the current window, and these 2 elements which are present here can be the minimum element of the subsequent windows. And the elements whose possibility of being minimum is 0 for the current window and the next windows are removed instantly, right? So this is the whole logic here. So when we will retrieve the front element here, it will be equal to 1. So we will just do a XOR of the existing result with this 1. That is, since the existing result was 0 as of now, so I will do a 0 XOR 1, which will be equal to 1 only. So the result value will be equal to 1 after processing this first window. So I hope you got this. Let us now move forward to the next windows, right? So now we will handle the remaining windows one by one separate. So this is our second window, right? So as of now, our window was this, and now we want to include this 3 and exclude this 5. Right, so how we will do this? So first what I will be doing is I will be excluding the contribution of this 5, and then I will be adding the contribution of this nums of I. So if I want to exclude the contribution of this 5, then it means that if this 5 is present in the current window or in this DQ, then I just have to remove it, because DQ only holds those elements that are a part of current window, right? But since now we know that this nums of I minus k, that is this 5, is not the part of the current window. So if it is present in the DQ, then we have to remove it. So we will just check if this 5 is present in the DQ or not. So this is the status of my DQ from the first window, and now we are watching that if this 5 is present or not. So one can clearly see that this 5 is not present. Why? Because we have erased it here only, right? So that 5 was never propagated further. So since this 5 is not present in the DQ, so we will do nothing, and the status of DQ will remain same like this. So in this way we have removed the contribution of nums of I, or checked the contribution of this nums of I equal to k, that if it is present in the DQ or not. So if it is not present, good, but if it was present, then we should have removed, right? So now we will add the contribution of this 3 here, and in order to add the contribution of this 3, it means that this 3 will now be a part of our current window, and in our current window these 3 elements are already present, and now we are adding this 3 here, right? So when this 3 will come, we will compare one by one with the elements present in this DQ. So we will compare this 3 with this 4, and after comparing this 3 with this 4 here, which is present here, we will be very sure that this 3 element is definitely less than this 4. So for the current window, since both of these elements are a part of current window and this 3 is less than this 4, so it means that this 4 can never be the minimum of the current window or the remaining windows anymore, because as long as the windows are considered, this 3 will always be present along with this 4, right? Because the window will slide forward, so both these 4 and 3 will always be present together, and as long as both of them will be present, this 3 will always be less than this 4. So that's why the probability of 3 being minimum is always more than this 4. So it means that there is no purpose of storing this 4 anymore in this DQ. So what we will do, we will simply erase this 4 here, and after erasing this 4, we will again compare this 3 with this 2. But now after comparing, we will realize that this 3 is actually bigger than this 2. That is, for this current window, now we will realize that this 3 cannot be the minimum, but it may be the minimum for the remaining windows when this 1 and 2 will be excluded, right? So that's why we will just do a pushback for this 3 here like this. So we have earlier erased 4 because we were sure that this will never be the minimum of any window, but after comparing this 3 with this 2, now we realized that this 3 is actually bigger than this 2, so it will definitely not be the minimum of the current window, but it may be the minimum of the subsequent windows. So we'll just do a pushback in order to check for future, and after doing that, this will be the status of our DQ, having this and these elements. And again, you can see that these elements are present in sorted order in this direction, and since they are sorted, the minimum element will always be present at its front. And here also you can see that for this window, the minimum element is this one here, which is stored at the front of the D. And now what we have to do, we have to take the XOR of this one with the existing result. And since the existing result here was 1, so I will do a XOR of 1 with 1 only. That is 1 XOR 1, which will result into 0. So that's why our result will be 0 after processing the second window. So in this way we will handle the second window, and now let us move forward in order to tackle the third window. So this will be our third window, and as of now, the status of the window is this, and now we want to remove the contribution of this one, right? So in order to remove the contribution of this one, since this is our DQ here from the previous window, that is 1 to 3, that is this, right? So the status of DQ is this, and now we want to remove this 1 from this DQ. So we will check if this DQ is holding this 1 or not, or DQ is holding any elements less than or equal to 2 index or not. So if it is holding any elements of this region, then since they are not a part of current window, then it means that they should not be present in the DQ at all. So here we will check, and after checking we will realize that this one which is present at the front is having an index of 2, which is not a part of current window, because we know that our current window only starts from 3. But since this one is having an index of 2, so it means that this one must not be present in the DQ anymore. So what we will do, we will do a pop front here, and after doing the pop front, this will be removed, and only this 2 and 3 will remain like. So in this way we decreased or removed the contribution of this nums of I minus k from the DQ. And after doing this, now we want to add the contribution of this 7. Now since this 7 is a part of current window, right, so we will compare it with the elements present in this DQ one by one from the back side. So after comparing this 7 here with this 3, we will realize that this 7 is greater than this 3. So it means that this 7 can never be the minimum of the current window, but it may be possible that in future this 7 can be the minimum of the remaining windows, right? So that's why we will just insert this 7 into the back of the DQ like this, right? And after doing this, this will be the status of my DQ consisting of 2, 3 and 7, right? So only those elements are present in the DQ that can be the minimum of current window or the remaining windows. But since this 4 can never be the minimum anymore, we know this, so that's why this 4 is not present. And again we will see what is present at the front of this DQ. So since 2 is present, so we will do a XOR of this 2 with the existing result. And since the existing result was 0, so I will do a XOR of 0 with 2, which will result into 2. So that's why after processing the third window, our result is 2. And in this way the third window is also done. And now we are moving on to the fourth window. So this is our fourth window, and right now the window is this, and we want to remove this nums of I minus k from the DQ, right? So we will check if any element of this region is present in the DQ or not. So if any element of this region is present in the DQ, it means that they are not a part of the current window, so they must be removed from the DQ. So we will start checking from the first, right? So since at the start of the DQ right now 2 is present, that is this element which is having an index of 3, so we know that this must be removed because this is not a part of current window. So we will just do a pop front in order to remove it, and only 3 and 7 will remain. And again we will check the index of this 3. So since the index of this 3 is 5, so it means that we will stop now, because this 3 is a part of current window because its index is definitely greater than or equal to 4, and we don't need to check any further because the index is increasing in this direction, right? Because the elements are present in sorted order for the current window. So that's why we will only pop front this 2, and this 3 and 7 will remain. And now we want to add this nums of I, that is 2, right? So now we know that this 2 is a part of current window along with these elements, right? So since this 3 and 7 are present in the DQ, and now this 2 is being a part of the current window along with this 3 and 7, so we will compare this 2 with this 7 first and then this 3 first. So after comparing this 2 with this 7, we will realize that this 2 is less than this 7. So it perfectly means that this 2 can be the minimum of this current window, but this 7 cannot, neither for the remaining windows, because this 2 is now coming along with this 7. So this 2 is less than 7, so this 7 cannot be the minimum of any window now. So we will just simply erase this 7 and only 3 will remain. And now we will compare this 2 with this 3, and again after comparing this 2 with this 3, we will see that this 2 is now less than this 3. So for the current window, this 3 cannot be the minimum anymore, but this 2 might be the minimum, right? So that's why, since we are sure that this 3 can never be the minimum anymore, so we'll simply erase this 3 from our DQ, and this 3 will also be gone now. And since no element is present in the DQ anymore, so we'll just push back this 2 now, and after pushing back, this 2 will come in the DQ as the only element, right? So I hope you are getting what I am doing here. It's complete maths. So after doing this, that is removing the contribution of this 2 from the front, and while adding this 2 here, we realized that this 7 and 3 cannot be the minimum of the current window or the remaining windows anymore, so we simply erased them, and in this way only 2 is remaining in the DQ now. So what we will do, we will take a XOR of existing XOR with this result. So since the existing result was 2, so I will take a XOR of this 2 with this 2, which will result into this 0, and in this way our last second window is also done. And now we will move to the fifth window. So this is our fifth window here, so pay attention. So this is our fifth window, and currently the status of our window is this, right? So we want to slide it from the fourth window to this fifth window, that is we want to remove this 4. So if you want to remove this 4 first, then we will check if this 4 is present in the DQ or not. So since this is the status of my DQ after processing the fourth window, in which only 2 is present, whose index is starting from this 7, right? So we will see that this 4 is definitely not present in this DQ. So since this 4 is not present in this DQ, so it means that it is already absent in the DQ. So we don't need to do anything further, right? So in this way, the contribution of this nums of I minus k is also handled. And now we will try to add the contribution of this nums of I, that is 1. And now we are pretty sure that this 1 is a part of our current window of size 4, right? So this 1 is now a part of the current window, and in this window as of now 2 is also present, right? And now 1 is also getting added, that is 1 is also present. So we will compare this 1 with this 2, and after comparing we will realize that this 1 is definitely less than 2. So since this 1 is definitely less than 2 and both are present in the same window, so it means that this 2 can never be the minimum anymore, because this 1 has come now which is less than it, and they are both present in the same window. So that's why we will simply erase this 2 from the DQ. So I will erase this 2, and after erasing it, the DQ will get empty, and I will push this new possible minimum element into the DQ, and after pushing it, this will be my new DQ, right? And since after erasing this 2, the DQ became empty, so it means that there was no element anymore present in this part for which we could have compared it with 1. So if any more elements would have been present, then we would have definitely compared it with this 1, so that 1 would have been placed into its perfect position. But since after erasing this 2, the DQ became empty, so it means that there are no more elements to compare this 1 with anymore, so we simply added this 1 into our DQ. and after adding it, this 1 is the only element in the DQ. So we will check the front of this final DQ now and see what is the element present. So since 1 will be present at its front, so it means that for the current window or for the fifth window or for the last window, the minimum element is nothing but this 1, which is present at its front here, which is 1. So what we will do, we will take a XOR of this 1 with the previous result, and since the previous result was 0, so I will take a XOR of 0 with this 1, that is 0 XOR 1, that is 1, which is our final answer also. So that's why after processing the last window, our result is equal to 1. So we will simply print this one. So this is the whole logic behind this problem here, right? I hope you got every single point, because everything is very logical here, right? But before moving to the coding part, I want to tell you something, and I have purposely not tell you that while explaining the concept, because you might have got confused, but I will explain you that thing now. So the thing is that in the DQ you were seeing that I was storing the actual elements, right? So this 2 was the actual element, this 1 was the actual element, right? So to make you understand, I was actually storing the actual elements, but while implementing the code, we will not do this. So what we will do, we will always store the index of an element in DQ instead of the actual element. But why? Because using index, we can go to the element. So if you know the I, we can go to the nums of I, right? But from the element, we cannot go to the index. So if you know nums of I, then you cannot determine I, right? And why this is important? Because when we were removing the contribution of this nums of I minus k, then how will you determine where this 4 is present in this DQ or not, right? So in this example, since we want to remove this 4, so now here it is visible to you that this 4 is not present, but how logically will you determine here? So if the indexes are stored in this DQ, then what we will do is we will check from the front that if any element has an index of less than or equal to 4 here. So if any element has an index of less than or equal to 4, it means that they belong to this region and must be removed from the DQ. Then we will simply remove them. But if only the elements are stored at the front directly, then how will you determine that if they belong to the current window or not? So you will not be able to determine. So you can see here also, since we wanted to remove this 2 here in the fourth window, so in order to remove this 2 from the current window, which is present here now, we would have checked if there is any element at the front having an index of less than or equal to 3. So instead of this 2, if its index, which is 3, was present, then we would have simply checked if this 3 was equal to this less than equal to 3 was or not. So since this 3 would definitely be less than equal to 3, so it means that the element present at this part belongs to the previous window and is not a part of current window. So in that case, we would have simply pop fronted it. And for the next element, which is 3 here, so instead of this 3, its index would have been present, which is 5. But we will see that this 5 here is not less than or equal to this 3. So it means that the elements from this 3 and afterwards are having an index of greater than or equal to 5 and not less than or equal to 3. So we would have simply stopped pop fronting it, right? So that's why using index instead of element is very essential in order to make sure that we pop front only those elements that are not a part of current window, because using only the values of those elements will not help us in order to determine which element to pop, right? So that's why it is important to use the index in the DQ instead of the actual element, so that when we want to remove the contribution of this nums of I minus k, we can do it easily, because we just have to compare the index of this nums of I minus k. So if it is less than or equal to the threshold value, then we will simply remove it, and we will keep doing it until every element of the previous window is removed. And once the element of current window comes, we will simply stop. So that's why indexing is important here. So let's move to the code part and see how this will be coded. So suppose this is my array here and this is my k value, that is the size of the window, right? So we will store our final result in this XOR variable. So this is our result variable, and here I am initializing a DQ, and since initially we know that we have nothing to compare the first element with anything, so I am just pushing the first element here like this. And since we want to insert the index instead of the actual element, so that's why here I have pushed the index of the first element, which is nothing but 1. So after the DQ is initialized like this, we will handle our first window, and in the first window, since we have already dealt with the first element, so it means that now we have to move from 2 to k. So we will just check if DQ is not empty and the element that we are inserting is less than or equal to the existing element. So if it is less than or equal to the existing element, so it means that the existing element cannot be the minimum anymore. So we will just do a pop back of it, right? And after doing a pop back, we will simply push this new element into the DQ like this. And after every element is processed for the first window, whatever result will be there, that is whatever will be present at the front of the DQ, we'll simply take a XOR of it with the result like this. So in this way our first window will be handled. And now we'll move to the next windows. So for this next window, we know that the next element is nums of I and the previous element is nums of I minus k, right? So what we will do first, we will try to remove the contribution of the previous window, right? That is, remove the contribution of nums of I minus k. So what I will do, I will simply check if the DQ is not empty and the element present at the front is having an index of less than or equal to I minus k or not. Right. So if the element present at the front of the DQ is having an index of I minus k, so it means that it belongs to the previous window and should not be the part of the current window. So we will do a pop front, and instead of writing this statement, what you can do is, instead of writing this while, you can just write a if condition, because this will be at most executed once, right? So instead of writing this while, you can just write a if, and also this less than is not required. You can just write a double equal to in order to compare the front index with the I minus k, right? But this is the standard way of writing the code. But if you are solving this problem, then you can definitely write this while with this if and remove this less than sign with this equal sign, because at max only one element will be removed from the front, right? So once the contribution of the previous element is removed, now we want to add the contribution of the next element. So while adding that is, we want to place the new element at the perfect position in the DQ. So we will start comparing this new element with the elements present in the DQ at the back one by one. So if this new element's value is less than or equal to the element's value that is present at the back of the DQ, so we will remove that element that is present at the back of the DQ. And we will do this until our nums I becomes greater than that back element. And once that happens completely, we will simply push this new element, that is nums of I, that is do a push back into this DQ, so that after both of these two operations has been done, our DQ will be present in sorted order, right? And after that, whatever element will be present at the front of the DQ, we will simply extract it like this, because since we are storing the index, so we have to do a nums of this index in order to get the element. And after getting the front element, we will simply do a XOR with the existing result here. And in this way, all the remaining n minus k windows will be handled. And finally, I will print this result here. So this will be the whole coding logic, right? So I hope you got every single point that I told you in this video, right? So yeah, thank you so much for watching this video. Thank you.